Let's kick things off with some insight into patent searching and the intellectual property landscape. Before we jump into any searches, I want to take a moment to adjust the settings. The settings in SciFinder allow for customization, for example, of how the filters appear, tailoring them to your preferences. You can choose individually which filter will be located, or you can also choose between a research focus or an IP focus. Let's do this. Override the filter order and save. Now let's go back to the landing page and start our first search. I have a specific structure in mind for my search, but instead of conducting a substance search, I aim to find publications related to this structure for treating or diagnosing neurodegenerative diseases like Alzheimer's or Parkinson's. I'm not using a Boolean search. Instead, I'm entering a concise phrase regarding treatment or diagnosis of Parkinson or Alzheimer. The results show 6 entries, including 2 as drawn answers. For those familiar with SciFinder prior to the Search Sense launch, you may recall receiving extensive results, especially for keyword-rich queries, due to the inclusion of partial hits. That is no longer the case. The query interpretation now indicates that treatment or diagnosis are keywords included as alternatives, and the topics of Parkinson and Alzheimer are combined with the AND operator. This is a straightforward display of how the query was interpreted. Additional synonyms have, of course, been taken into account. SciFinder prioritizes OR before AND when processing results, so the outcome is as intended. I mentioned in the beginning that I will focus on updates relevant to IP searching. A comprehensive search often requires multiple strategies. To maintain an overview of the results obtained, we can save them individually and combine them later with the combine answer set functionality. But we can also add them to the same project. I'm going to mark them all, add to the projects. Let's give this a new name. When we add identical publications from multiple searches to the same project, they will not appear multiple times. So we don't have to worry about duplicate documents cluttering our project. So what are other search strategies that we can employ? Publications come with keywords like the CAS concepts, abstracts, and classifications. These classifications include IPC and CPC codes, which categorize patents by topics. These codes are assigned by patent offices, not by CAS, and we can utilize both for our searches. Let's return to the landing page and edit this search to make it an advanced search. We still have our structure in here. I will reduce the keywords just to Alzheimer or Parkinson And now I'll incorporate the relevant patent classification code. That is specifically A61P2528. If you prefer not to use the exact code, you can broaden the scope without the need of truncation. We now have 10 results. I've simplified the query, which does broaden the search a little bit, but we also have uncovered publications that weren't retrieved solely through keywords and structure, but because of the relevant classification codes. Let's add these to our projects. Now, let's take a closer look at one of the patents. What information can you access within SciFinder without needing to dive into the full text or other sources? You'll find a substantial list of content available. I won't cover everything, but I'll highlight a few key points. There is a summary on the top left corner, and don't forget that patent pack is an enhanced view of the full text, including the locations of all of the individual substances. Patent family tables can vary in length. Some families may have 20, 40, or even 60 members. It's beneficial that we can filter or sort these by jurisdiction and patent status, allowing you to focus on what's relevant. We've also recently added the claims text, which is available in English. Currently, this text isn't searchable, but it is there for your review. I've already mentioned the classifications, and I'm sure that you are familiar with the CS concepts. We have added descriptions to most of the concepts. They are included along with a list of synonyms that are automatically searched. You can also explore these in the CS lexicon, where you can view broader categories or more specific, narrower concepts. This exploration can help identify additional keywords or provide context for your subject. A new feature we've introduced on the patent detail page is the Makush structure. They visually represent a wide variety of potential substances generically described in the patent. Since these can number in the millions and may not have been synthesized or specifically investigated, they are indexed in such Makush structure way rather than individual substances. You can now view these descriptions within SciFinder without needing to consult the full text. Considering Makush structures as relevant answers is another strategy for a comprehensive search. Let's see how we can implement this. I'm rerunning my original query and navigating to the Patent Makush tab. A Makush search focuses solely on structure, ignoring keywords that have been entered, as indicated by this node. We have 178 substructure results, potentially from the same number of patents or less, because one patent can contain multiple Makush structures. Some of these may overlap with the results of our previous search, for instance, the patent from Tübingen we just examined. In order to have all filters available, we will cross over the Makush results into a reference answer set. So that's 154 patents, which we need to refine further because the keywords we have added have been lost in this Makush search pathway. So this does give us, again, 10 results. Let's move these to our projects. And in the end, we will review our project folder. We have a total of 18 references. Throughout the 3 different queries, we never encountered an answer set where 18 was a total. We had 6 and 10 previously. That indicates that from the various searches, we do have unique answers. The largest answer set isn't necessarily the most complete. For comprehensive results, often but not only relevant in the IP search field, it is essential to examine a topic from multiple perspectives through multiple queries. From this project, you can share the results with others. For example, grant access to fellow SciFinder users for review or also modification. Or you can download it in a file type of your choice, for example, an Excel list with basic identifiers or more detailed information, including abstracts for offline review.
Before we get started, I'd like to mention that the version of SciFinder I'll be using today is a training environment. Some elements you may see are part of our internal training setup, and certain features, including CAS Sneakman, are not available to regular customers. The functionality I'm demonstrating reflects the core enhancements relevant to users, but the interface may look slightly different from production accounts. With that said, today's session focuses on strengthening 3 critical areas that directly impact scientific research workflows: transparency in how searches are interpreted, clarity in how results are presented, and efficiency in synthetic planning. In modern research environments, speed matters, but clarity and confidence matter just as much. Researchers need to understand how their query was interpreted, why specific results were returned, whether the system captured their scientific content, and how quickly can they move from search to decision. The enhancements I'll show today are designed to improve the entire experience. Today we'll cover enhanced query interpretation for class-based substance search, result interpretation visualization, reaction query interpretation transparency, interactive retrosynthesis improvements including enhanced cyclization handling, and streamlined retrosynthesis workflow. Let's begin with a property-based class search. So what I would do is go ahead and type in melting point of ketones and go ahead and click on search. So this query combines a chemical class, which is a ketone, and a physical property, which is a melting point. So immediately you'll notice 2 things. The query interpretation panel on the upper left-hand side, and a very large result count at about over 16 million. So why 16 million results? That large number reflects the scope of what we're asking. We are not searching for a single compound. We are asking for all ketones with melting point data across all index substance records and associated content. Ketones represent a massive chemical class, including aliphatic ketones, aromatic ketones, fused ring systems, pharmaceutical intermediates, and material-related compounds. When we combine a broad structural class with a widely reported physical property, the data set naturally becomes very large. This is expected and appropriate for this type of conceptual search. So if we click on the query interpretation, notice how SciFinder explicitly shows the functional group for ketone and the property intent that is searching for, melting point. This transparency is critical. When result sets are large, confidence in how the query was structured become very important. This enhancement ensures clarity, reduces ambiguity, and improves reproducibility. Now let's examine how the results are structured. Beyond the query interpretation, the system now provides enhanced result interpretation visualization for substance searches. When working with a large dataset like this, visualization becomes essential. Researchers need to quickly understand what's included, what structures align with the intended class, whether the property is consistently captured. So we can see variables in the different type of ketone class as we scroll down the page. But we've also analyzed the results based on the reaction role, the top reference roles, if it's commercially available, the number of substances of components, the elemental composition of each of the compounds, the top substance classes, the top polymer classes if they are polymers, and the experimental spectrum availability. And so here we can actually see melting point, it's at the top. So out of these 16 million results, only 649,000 of them contain experimental melting points. So this enhancement reduces validation time. Instead of manually opening multiple records to confirm alignment, the structural and property organization helps users move more quickly from search to analysis. For class-based property research, this is extremely valuable. So I'm going to go back to the home page. And now we're going to shift over to reaction searching. So what I would do is I'm going to type in oxidation of benzyl alcohol to benzaldehyde. And I'm going to click on search. So reaction phrasing can vary widely. Here, SciFinder displays, under the query interpretation, the reaction intent, the recognized reactant, the recognized product, and it's all controlled reaction terminology. So the reactant is benzyl alcohol. The type of reaction that we're doing is an oxidation. The product is benzaldehyde, and we can see that the functional group is benzaldehyde as well. This transparency ensures correct structural mapping and reduces ambiguity. For synthetic chemists and process teams, this improves confidence and reduces iterative searching. So now let's go ahead and move on to the next topic, which is the interactive retrosynthesis. So what I'm going to do is I'm going to just go ahead and search it on the search sense bar, and I'm going to type in tetrahydroisoquinoline and click on search. So we noticed that we get 166 substance records, which tetrahydroisoquinoline being the first as we searched it. This reflects structural specificity. SciFinder is returning a distinct record corresponding specifically to tetrahydroisoquinoline and closely defined variants, not every substituted analog. For today's purpose, this focus scalpel is ideal for demonstrating the retrosynthetic logic. So now what I'm going to do is I'm just going to copy the CAS registry number. I'm going to go back to the home page. I'm going to start the retrosynthetic analysis. I'm going to click on paste and I'm going to click on draw, and we can see our tetrahydroisoquinoline. And I'm going to go ahead and start the retrosynthetic analysis. Now, My target molecule is below my cost limit, and it says no plan provided. So I'm going to continue with a reduced cost limits to explore suppliers for this target and choose a different structure. I'm going to go ahead and continue to the retrosynthesis just to show what features have been included. So when the system detects a ring system, cyclic rules are boosted. Notice how the plan prioritizes ring-forming disconnections, intermolecular cyclization strategies, chemically intuitive pathways. This is particularly important in medicinal and heterocyclic chemistry. Boosting cyclic rules improves synthetic realism and accelerates route evaluation. As we can see, if we pick this route here, right, this is a cyclization reaction. We can actually see the cyclization reaction, and we can see all the alternative steps for that cyclization reaction. So if that synthetic path was not feasible, and an alternative step is feasible, you can exclude that step, replace it with the alternative step, and rerun the retrosynthetic analysis. Previously, users configured constraints before generating the plan. Now this plan runs automatically using default parameters. The shift to workflow, generate, review, refine, rather than configure, generate, review. This mirrors real-world chemistry workflows and reduces friction in exploratory research. So, as I will demonstrate, if we edit the plan under the selected options, we have the option of changing the rules for the predicted reactions. So common organic synthetic rules, uncommon synthetic rules, and then rare, which combine both uncommon and common. You're allowed to either break or protect a bond via in green, and we can protect the bonds in red. If I continue to the retrosynthesis plan, that retrosynthesis plan will now take that bond breaking and bond protection into consideration. So to summarize, these improvements are transparency in search interpretation, clarity in a large result set, confidence in reaction mapping, chemical relevance in retrosynthetic planning, and overall workflow efficiency. From large-scale property searches returning millions of results to focused scaffold-based retrosynthesis, the system now provides greater interpretability and smoother workflows.